I'm Qi Zhang, and I'm a senior in Leverett House. I study computer science, and I'm a TF for CS50. As a freshman, I didn't even have a laptop or a smartphone. I had no programming experience. CS50 was the most memorable course that I took at Harvard because it was a struggle, but it was a really fun struggle at the same time. And I made a lot of amazing permanent friends, and I learned a lot of really applicable skills. I'm just so glad that I didn't let my lack of background be an excuse for me not to take CS50. I'm Qi Zhang. I'm a senior in Leverett House, class of 2014, and I took CS50.
So this is CS50. This is the end of week 0. And recall where we began last time was with these lamps, which were so popular that we went and bought some more today. So I think this will be our thing this year. Desk lamps if you come up on stage, at least until we run out. But we use these, recall, to introduce the basics of representation of data, right? We needed a way to start representing information inside of a computer. And the simplest way to do that was with one ingredient, electricity. And the simplest thing you can do with electricity is turn it on and turn it off. Let the electrons flow or not. And using those two basic states, off and on, or false and true, or 0 and 1, we began to see that we could build up, in this case with light bulbs, more numbers than just 0 and 1. We counted as high as 7, for instance, last time. But all we have to do is keep throwing more and more light bulbs at that problem. And really, we can represent any number that we might possibly want. Well, we transitioned quickly then on Wednesday to this byte of volunteers. 8 bits is what we generally call a byte. So here we had 8 volunteers on Wednesday who collectively were representing 8 bits. And when their hands went up, they were a 1. And when their hands were down, they were a 0. And we had these folks come up on stage. Why? What were we able to do with this sequence of bits? So create an alphabet. We were able to build on top of that previous lesson learned and actually start to make more interesting information that's at least more familiar to us humans. And this is going to be a recurring theme throughout 50, but also computer science more generally, this idea of layering, where at the end of the day, if you really start at the basics with a computer, yes, it's zeros and ones. And beneath that, it's just electricity. But we very quickly start to take those low-level details for granted and start to layer on top of past work done so that we ultimately, by the end of the semester, and really more generally as computer scientists and programmers, can do some really, really powerful things by leveraging work that we ourselves have done and also standing on the shoulders of others. Now, we quickly transitioned on Wednesday from just needing to represent information to wanting to do something with it. So what did we define an algorithm as? Series of instructions. So it's a series of instructions, a number of steps that you, a human, or a computer, more typically, would execute one after the other in order to achieve some goal. And we had a few goals last time, one of which was to count people in the room. And another such example was to find Mike Smith in a phone book. So you may recall that I tore a phone book in half toward this end of finding Mike Smith. The purpose of that visual was to demonstrate, again, that we were literally tearing this problem in half, and very quickly going from like 1,000 pages to just one single page. Those of you who missed us on Wednesday thought we'd play back some footage of what you missed. Let's take a look.
Go, 1,500 pages, nice clean line, legitimate tear.
So that was Wednesday. We transition, though, on Wednesday now to wanting to represent algorithms in some semi-standard way, not just describing them verbally, but trying to express them in writing or on a computer screen so that we could begin to improve upon and modify them and eventually actually analyze just how correct or how fast they were. So we introduced this notion of pseudocode, which in layman's terms was what? OK, words. Let's go a little deeper than that. English, sure, but toward what end? Words with which to create or to represent algorithms. So there's no one language known as pseudocode in the world. It's just that you in English, or whatever your spoken language is, use a sort of cursory notation to convey an idea very succinctly. But we'll see that certainly with an English pseudocode, and it turns out most programming languages themselves are derivative of English itself, we'll find that there's some standard ways of representing pseudocode and also programming code. So as you begin to see even the simplest examples today, realize these same patterns will recur next week. So pseudocode was some kind of language resembling a programming language. And the first example we saw visually written down was this one. It was only a 3-step program, the goal of which was to count the number of people in a dorm room, per that video on Wednesday. But there were a few interesting aspects of this simplest program, and these will be recurring themes. So for those unfamiliar with this, one, we introduced a variable, and probably everyone in this room is familiar with a variable in the context of algebra. But here in programming, variables are, one, can be called anything we want. We've been using n as a counter, but we could use the word counter, or as you'll see, most any phrase that you might like, so long as it's descriptive. But it's really just a storage container. It's a chunk of memory, some number of bits, and it varies by computer how many bits there are that compose that variable. But we can put values in it. Thus far, we've only put numbers, but we can put actual words. We can put paragraphs. We can put images. Anything really we can represent with zeros and ones, we can put in this higher level notion of a variable. So pretty straightforward there. But that's line 1. But we very quickly moved on from line 1 to actually do something with that variable. And in line 3, we updated n. We incremented n. And we could write this any number of ways. But perhaps the most obvious is just to say set n equal to whatever n is plus 1. So that was our increment. Meanwhile, there was a loop. And this one, too, is probably pretty intuitive. A loop is just something in a program that happens again and again, some kind of cycle. And this key phrase here, for each, is actually very common throughout most programming languages, including ones we'll see in the course. Anytime you see the word for, it typically conveys the idea that a loop, something cyclical, is about to happen. But it's worth noting one other syntactic detail. The fact that the third line there is actually indented by having hit the space bar a few times is deliberate, because human convention is such that when you're doing something again and again in a loop, as begun on line 2, you indent anything that belongs to that loop just to make clear that it's line 3 and not, for instance, line 4 or 5, if there were lines 4 and 5, that are part of that loop. So this simple indentation conveys that basic idea. So we applied this algorithm now to a few examples. And this, too, simple example in the real world, but it's going to be representative of how you would go about testing your own increasingly complex programs. You try a few scenarios, some representative inputs, and see if you get the desired output. So this example had 2 people sitting in the dorm room. On the left is that same pseudocode, and this is a screenshot of the very last step of the application of this algorithm to those inputs, where there were 2 people in the room. And recall, as we step through lines 1, then 2, and 3, and 2, and 3, and done, by the end of that algorithm, we had indeed counted the 2 fellows who are in the room. So then we tried another example. We said, what if there are 0 people in the room? Is this code still correct? And indeed it was. It just so happens that line 2 and thus line 3 are not going to execute. They're not going to happen at all because they're just not applicable if there's 0 people in the room. But not a big deal. Line 1 initialized n to 0. So even though only one line of this program actually ends up being useful, it still yields the correct answer, as indicated by the orange 0 at the bottom. But then we decided that was a kind of a stupid algorithm. It was pretty slow. Surely I can do 2, 4, 6, 8, 10 when counting people in a room. So we tweaked the algorithm, the pseudocode, to say now in line 2, for each pair of people in the room, proceed to, in line 3, increment n by 2. On each iteration. So that would have worked here for this pair of persons in the room. But then if you start thinking about this, and it doesn't take long to realize, wait a minute, this is going to break, it breaks at what simple case? If there's 3 people in the room, or more generally, when there's an odd number of people in the room, including 1. We would miss that person here because there are no such pairs. So we quickly redressed that by instead introducing what additional programming construct to the pseudocode? So a condition, we called it, or a branch. And it's meant to convey visually that idea of branch, a fork in the road where you can either do this or maybe something else. And indeed, we address this issue by adding line 4, by saying really at the very end, if one person remains, then go ahead and count them special. So you sort of special case them, so to speak, so that now we can handle both an even number of people and an odd number of people. Now, there are any number of ways we could have expressed this, and frankly, I could have been even more nitpicky when it came to my choice of English for the pseudocode, but at least the spirit of the idea is conveyed. If you handed this code to a friend who's not in CS or has never taken CS, odds are they could figure out, given 3 people in the room, how to count those people based on these instructions. And that's all really we wanted to achieve with pseudocode, was somehow standardize how we're going about representing ideas so that we can begin to do more complicated things still. So that leads us then today to actual code. We begin to program today, albeit in a friendly environment, and then next week we transition very quickly to a more arcane syntax, but one that you'll see is fundamentally the same as the ideas we'll see manifested with this other language today. It's just going to look a little different. So rather than just call this code, I'm going to be a little more precise and say henceforth when writing a program, you're writing source code. It's kind of like pseudocode, but we'll see it's not sort of loose when it comes to choosing the words that you use. When programming in a language, you have to use the words, the phrases, the syntax that other people have decided represent that particular language. So pseudocode's up to you. An actual programming language like C, as we'll eventually see, is standardized by other people. So how do we go about writing some source code? Well, I'm going to go ahead and do this. I'm going to go ahead and open up a window here. More on this next week, but this is a device called the CS50 appliance. I'm running a piece of software on my Mac, though you can do the same thing on a Windows computer, that is giving me the illusion of running a different operating system altogether right here in a window on my Mac. I've just full screened it so you don't actually see Mac OS right now. This is an operating system called Linux. It's very popular, it's very fast, it's very free, which has made it very compelling, especially in the commercial world, and more on that toward the end of the semester when we use Linux quite a bit for web programming and hosting of actual websites and projects. So for now, just know that this is a desktop that's meant to look vaguely familiar to Windows and Mac OS. It just has some different names and icons for things. But this is the so-called CS50 appliance, a virtual machine that starting next week, you guys will run inside of a window on your own Mac or PC. For today, I'm going to open up the simplest of programs. It's called gedit. And this is just a graphical editor. It's kind of like Microsoft Word, but simpler. It's kind of like TextEdit or Notepad. It's just a very simple program with which to write words on the screen. It just so happens if I save files that I create with this program in a special extension like .c instead of .doc or .xls or whatever you're familiar with, I can actually create programs using even this simple text editor. So let me do that. Let me go ahead and save this file first as hello.c. And again, this user interface will become familiar to you quickly. But for now, I'm just typing in a file name. I'm going to save it into my John Harvard home directory. And now I have this tab that indicates I'm indeed editing a file called hello.c. So nothing too interesting yet. And now it's going to get pretty cryptic. I'm going to zoom in just so it's more visible. And I'm going to start typing include standard io.h int main void open curly brace, 1, 2, 3, 4 spaces of indentation, printf for print something formatted, quote unquote, hello world, \n, close quote, close parenthesis, semicolon, enter, backspace, 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 close curly brace, I have programmed. All right, so this is a super simple program, really the program that anyone starts off programming with. And all it does, for all its complexity, is print out on the screen, guess what? Hello world. But it's not sufficient just to write a program. So this is code. This is source code in a language called C. It's saved currently in a file called hello.c. Now look at the bottom of the screen here. More on this again in the weeks to come. But this is what we'll call a terminal window. It's a blinking black and white prompt. It's sort of an old school interface to a computer that generally doesn't use a mouse or other graphical elements. It just uses your keyboard. And I can type commands at this blinking prompt. And for today's purposes, I'm just going to type the following: make hello. And that program, make is just a program that in the real world these days we would double click on. But in this interface for today, we're going to type its name at this prompt. Make hello is literally going to make me a program called hello. And it's going to do so by looking for a file, just by default, called hello.c. It's going to assume I want a C program by nature of how this computer is configured. So I go ahead and hit enter. I see some cryptic output, but this will become all too familiar before long. This happened to run a compiler, more on that in a moment, called Clang. But now I've got just another blinking prompt, and I can go ahead now and type // for uninteresting reasons we'll come back to next week, hello. So all of this effort thus far just to write the simplest of programs that as soon as I hit enter does that. So I have written my first program. So I'm deliberately poking fun at this very simple program for a couple of reasons. One, it's hard to get excited about taking a class if this is the end game, right? But more than that, there's a lot of distractions up here, right? The first time you learn to program, for those of you less comfortable, and even I, back in the day, when I first saw something like this, you can kind of figure that, all right, this is going to print hello world, but there's so much distraction. There's so much syntax on the screen that gets in the way of very simple, otherwise simple ideas. So what we're going to do today is we're going to put aside C and come back to that on Monday, and we're going to use a graphical programming language called Scratch. This is a programming language that I alluded to on Wednesday that's going to allow us to do the same kind of stuff, but turn a blind eye for today to the curly braces, the parentheses, the semicolons, and all of these stupid distractions that get in the way in this first day of some basic, pretty interesting ideas. So toward that end, I'm going to go back to my desktop over here and introduce you to the alternative to that program, which is going to look a little something like this. That's how we're going to implement that same program today. 2 puzzle pieces that, when interlocked and clicked on, will say to the world, hello world. So let's actually go there. So I'm going to go ahead and open a website known as scratch.mit.edu. And this will lead me to this website here. In advance, I've logged into this website. And the first problem set will walk you through some of these steps. I'm going to go ahead and click on my Scratch folder here. And this is going to show me some projects that I've actually created in advance. And it turns out that this graphical programming language not only is going to let us program by dragging and dropping these puzzle pieces, you don't even need special software. It's all embedded within a browser so that you can do this, in theory, on your computers right now, as some of you may well be, without even needing software like the CS50 appliance, which will come next week. So I'm going to go up to the top corner here and click on Create. And in a moment, I'm going to get a blank screen via which I can start programming in this graphical programming environment. But this time, it's going to be much, much simpler to actually do so. So in just a moment, when the Wi-Fi cooperates, we now have this screen. So a quick verbal tour, but I dare say, certainly when you dive into the first problem set, you'll find this all very accessible and fairly intuitive. But let's paint a mental picture for just a moment. So beneath this prompt saying save changes, you're about to see Scratch. This is a sprite, it's a character, and he lives on what we'll call a stage, this big white rectangle on which he can move up, down, left, right, and do really other types of actions. Meanwhile, in the middle of this user interface, we have a whole bunch of puzzle pieces. And you'll see that they say things like move 10 steps, turn 15 degrees, point in a certain direction. But there's categories of blocks up here, too. So if I go to looks, you'll see that there's other puzzle pieces that apparently will tell this cat to say hello, to think, to show himself, hide himself. If I go down to sounds, it turns out there's ways to play sounds like meow, to stop all sounds, to play a drum. So long story short, there's a whole bunch of puzzle pieces that allow you to tell this cat or any number of other characters what to do. But to make this all happen, you need to start programming. And this big white box or gray box on the right-hand side, this is where I'm going to actually drag and drop those puzzle pieces. That is my blank text window equivalent. So I'm going to go ahead and click Control in the middle. Or rather, let me start up at Events. Under Events, you'll notice a few things that are deliberately curved on the top in such a way that they probably don't interlock on the top with other puzzle pieces. And that's because they demark the start of a program, the start of a script, so to speak. So if I go ahead and drag when green flag clicked over here, and then I want this cat to say something at first, I'm going to go under the Looks panel, and I'm going to go ahead and grab the Say Hello block and drag and drop and let go so that it automatically interlocks there. And then notice I can click on the text and I can override it to be more specific, like Say Hello World. And now we have the program that I claim is equivalent to that much more arcane program I implemented in C a moment ago. If I go over now to this left-hand side, notice there's a big stop sign and a big green flag. Let me zoom in for clarity. And when I now click this green flag, you can probably guess what this first program's now going to do. So there, too, we're programming, but we're not actually getting bogged down in some of those syntactic minute details. But let's try something a little more interesting. Let me go into my Scratch folder here. And actually, let me open up a separate program here for just a moment. Maximize this window. File, Open. And I'm going to go into today's source directory. As always, you'll find today and onward that all of today's examples are accessible inside of the course's website. And I'm going to go ahead here and pick up a little something different. This one here, for which I need a volunteer. Who would like a desk lamp today? Okay, how about someone a little? Are you on the end? Come on down. Now, would you like to participate or just start with the guest lamp? Okay, excellent. What's your name? Vanessa. David, nice to meet you. So come on up, and Vanessa's going to take control of my keyboard for just a moment. And what I've done here, just for time's sake, because I realized the Wi-Fi was a bit slow, Scratch, the programming environment that we're using, can also be downloaded and run on your local computer. So what I did in advance of lecture, in case that happens, I downloaded all of the files we're about to play with so that they can run a little more quickly right here on my laptop. So that's why now I'm seeing a Mac-specific interface. So I'm going to go ahead and open up this one. I'm going to go ahead now and full screen the window. And as you'll see, we can very quickly, as this student did, one of your predecessors, go from Hello World to a much, much more compelling application. So here are the instructions. Oh, and we have one other thing. I thought it would be fun, since normally we'll be filming cameras this way. I thought it'd be fun if, Vanessa, we could see the world through your eyes. So here we have some Google Glass. We will only be giving away desk lamps today. So let me cue this up. All right, so touch this. All right, OK Glass, record a video. All right, Vanessa. Now, as an aside, has nothing to do with Scratch. If you look slightly up and to the right, you'll see the literal glass, and you should see a little rectangular window. You should see all your classmates being filmed right now, yes? OK, so that's fine. We'll release this footage later. For now, turn your attention to the screen here. And what your predecessor has done is put some instructions on the screen just by using like a paint program. So you're going to, in a moment, press the space bar to begin. And then some puzzle pieces are going to start moving up the screen. And you want to hit the arrow keys, just like in real DDR, in accordance with things lining up with those arrows. You've played this before. Yes. All right. Vanessa, go ahead and take it away.
Work it, make it, do it. Makes us harder, better, faster, stronger. That don't kill me, can only make me stronger. I need you to hurry up now, cause I can't wait much longer. I know I got to be right now, cause I can't get much stronger. Man, I've been waiting all night now. That's how long I've been on ya. You know how long I've been on ya. Since Prince was on Apollonia. Since OJ had isotoners. Don't act like I never told ya. You know how long I've been on ya. Since Prince was on Apollonia. Since OJ had isotoners. Don't act like I never told ya. Never told ya. Never told ya. Never told ya. Never told ya.
Nicely done. Here's your desk. So let's now take a step back from that. So clearly that's the end game, right? The end game is not Hello World, but you don't have to necessarily do things that are so interactive. You can also do animation. So for instance, another one of your successors made this program here, which tells a story more than it does implement a game. So let me go ahead and open up here, program in our same source directory from today. This one called, and let's start with A Cookie Love Story. And not to make this too academic, but as you watch this one, think to yourself, which of those simple programming constructs that we've talked about thus far, variables and loops and conditions, did your predecessor probably use just to implement some of the visualizations you see here? So I give you A Cookie Love Story.
the dice, it had to be. The only one for me is you, and you for me. So happy together, so happy together. How is the weather? So happy together.
All right, so there we had a cookie love story, but even there, even there, think about as those hearts went from the bottom to the top of the screen, there was actually a bit of randomness going on. And indeed, we'll see that even in the simplest of environments like Scratch, as in C, you can generate random numbers or the illusion of random numbers so that the game is a little more interesting than it might be if you had absolutely hard-coded everything. In the movement that you see there, there's some kind of responsiveness. As soon as the gingerbread man touches the gingerbread woman, she seems to move away. And so indeed, you can implement, in most programming languages, the notion of events, whereby if one hand touches the other hand, that can trigger some of your source code to actually execute. You can listen for such things on the screen. So let's take a quick tour then of some of the building blocks we can use to achieve some of these goals. So here's what we'll henceforth call a statement. A statement happens to be purple in Scratch, a little something like this, but that's arbitrary. A statement is just a puzzle piece, or more generally, an instruction that tells the computer to do something. A statement. So here's a simple example. Say hello world. Another one might be wait 1 second. So this puzzle piece, which is supported in Scratch, will let your characters pause for some number of seconds. This, too, is just a statement. Here next we have another more interesting one, play sound meow. And the little arrow means that in Scratch this is a drop-down menu. So you can import sounds, you can record sounds, and do other fun things in Scratch. And that, too, though, at the end of the day, is just a statement. But now let's introduce a more interesting piece, that known as a Boolean expression. Capital B, named after a fellow named Boole. And a Boolean expression is just a puzzle piece, or more generally, a piece of information that is either true or false, 1 or 0, yes or no. So it's just a pair, one of those two opposites. So one such Boolean expression in the world of Scratch looks like this blue puzzle piece, and it's asking a question, mouse down, and that can either be, of course, true or false. So with this puzzle piece in Scratch, will you be able to detect if the mouse is in fact being held down by the human interacting with your program? This one's a little more abstract, but those two white boxes are just for numbers. So you can do things like, is this number less than the other? And if so, Scratch will behave one way or the other. This one's a little more graphical. It's if the sprite, if the cat, for instance, is actually touching the mouse pointer. So if the little arrowhead is hovering over the cat, then this puzzle piece will evaluate to true. It will be true, in which case if you use this Boolean expression, as we'll see in a moment, in a branch, you can either do this or you can do that. Much like we had a condition that checked, is there one more last person in the room? If so, add 1. Otherwise, don't worry further. So a Boolean expression can also be ANDed together or ORed together. So you can combine Boolean expressions and say this and this must be true for the whole thing to be true. And here is a more real-world example. If you've used CS50 courses to do course shopping, these check boxes there, where if you check that box next to courses, that will say, yes, only show me courses for which the Q value is 4.5 or higher. If you uncheck it, no, don't worry about that. Or similarly on the right, doesn't conflict with courses I'm taking. That's either true or false. It's just a Boolean expression. So all this time when you've used websites with checkboxes, you're just toggling the equivalent of a Boolean expression on and off. So in what form do you use these? Well, in Scratch, we'll see in a moment that there are conditions that look like this, and that's kind of sensible because much like in pseudocode, we indented these sort of U-shaped puzzle pieces mean that anything inside of that U is going to execute or not, depending on where it is. So if Boolean expression, then whatever's inside will get executed. Meanwhile, there's an if-else block. So if you want a branch that goes this way or that, Scratch gives us that. And by this logic now, even though that puzzle piece is clearly too small to wedge something else inside of it, the Scratch puzzle pieces, they're just going to grow. When you drag and drop over something, it will just grow to fit whatever it is you're trying to do. So we can take two of these things and make a three-way fork in the road so that you either do this or this other thing, just by nesting them in that way. Of course, if you do that too much, it starts to get ugly. But at that point, you're actually probably not programming very well. And so that will be a recurring theme, too, that of style. Just how well do you actually format your code, or how well do you design your code? But more on that in the future. And now we have loops. There's a nice forever loop in Scratch, which literally means that. Do whatever's inside of this again and again and again. You can be more concrete and say do the following thing 10 times. You can also use variables. You can come up with any name in that little drop-down and say give me a variable called n and set it equal to some value. And then you can have functions, but more on those in just a moment. Let me go back to my Scratch interface, and let me go ahead this time, and let's go ahead and open up, let's say, an example from that's a little more interesting. Let me go ahead and actually, let me just make it myself. I don't need to open this one. Let me go to File, New. I'm going to go to Events. I'm going to go to When Green Flag Clicked, and I'm going to go to Sound, and I'm going to drag and drop this puzzle piece, play sound meow. It latches together, and now if I click the green flag, adorable. OK, so now let's do something a little more logical, just to demonstrate that we can for now. I'm going to unlatch this from that guy. I'm going to go to Control, and I'm going to grab a condition. So if something then, so look, that's how it looks there. So I need a Boolean expression. And let me go ahead and say, let me go to Operators. I'm going to do something slightly mathy just for kicks. I'm going to go in here and say if something is less than something else, go ahead and do something. So now, you know what? A random block. So notice how if I hover over this thing here, oops, that will snap in there. So now notice I'm starting to do something already more logically interesting. If a random number between 1 and 10 is less than, let's say 6. If I choose 6, that essentially means do the following with 50% probability. It's like flipping a coin. Now I can do something conditionally, and that something I'm going to do is play the sound. So now when I click on this green flag, it's like tossing a coin. It was heads or whatnot there. Let's do it again. Heads again. Heads again. OK, tails that time. So 50% of the time, if we do this infinitely long, we will get 50% meows and 50% silences. So there, just a basic building block that lets us do that. But this is kind of tedious that I have to keep clicking that button. So let's just drag and throw all of those away. If you drag them to the middle, they'll just delete themselves. Let me go up to Control. Let me go to Forever. And in this time, I'm going to do something minorly annoying. And let me go ahead and do Control, wait 1 second, just so it's not too grating. That's not natural. OK. And notice what's nice about Scratch, for those of you who have prior programming experience, you don't need to start and stop. You don't need to compile. You just change it, and the program will adapt dynamically. So this is getting a little interesting, but let's take it one step further. Let me go ahead and get rid of that program. That's what we'll call a bug in Scratch. He should not keep making that sound, so we will tell him to stop. All right, so now I'm going to go into, I'll let MIT know. We'll go over here to Forever. And now I want to do something again and again. I'm going to go into Control, and let's see, if I'm going to drag my if condition there. So now notice the logic. When the green flag is clicked, do something forever, but only do that something if this other thing is true. I'm going to go to, let's say, Sensing. And I'm going to go ahead and choose touching and drop it there. That's a Boolean expression. And now notice in this drop-down menu, there's some predefined values. So I can say, are you touching the edge of the screen, or are you touching the mouse pointer, the arrow on the screen? So I'm going to do that. And if so, then I'm going to go ahead and play sound meow. So now I kind of have the beginnings of a game, an adorable game. Oh, damn it. OK. An adorable, buggy game. Let me wait. Let's say 1 second there. Now play again by clicking the green flag. So now it's like petting the cat, right? OK. All right, now this one I did make in advance. Very late at night, it gets kind of easy to do stupid things. So let me go in here. Let's say that was pet the cat. Let's now open don't pet the cat. Now if we play this one, you can guess if you're looking at the screen. Now if I pet the cat. OK. So don't actually pet the cat in that case. So now we just have an example of a branch that's going in 2 directions. Now let me go ahead and open another one here. This one also among our source code files for the day. So let me go back into my source directory and go into, let's choose this guy here. and see what's different. Wow. All right, so now it's getting a little more complex. And before we see what this guy does, let's try to infer from the program at the right-hand side. And now Scratch clearly allows us to have multiple scripts, multiple programs associated with one sprite, with one character. And apparently, they're both going to run in lockstep. Because both of these programs starts with when green flag clicks, this is hinting at a more advanced topic with which some of you might be familiar, known as threading or multi-threading. Turns out, long story short, computers today can essentially do multiple things at once. Or they can do one thing at a time so fast that you don't even notice that it's actually doing one thing at a time. But for now, let's assume that both of these programs are going to execute at the same time. And notice both of them have forever puzzle pieces. So they're both going to keep running until I hit the red stop sign. So what are they going to do? On the left-hand side, I'm apparently declaring a variable called muted. So I didn't call it something boring like n. I called it muted this time to convey meaning. I set it equal to 0. Let's think of that as false. Or let's think of that as false. Now, forever do the following. If the keyboard's spacebar is pressed, then if muted equals 0, then change muted to equal 1, else set muted to 0. So logically, even though that's a whole bunch of puzzle pieces, that's just saying when I hit the spacebar, what should I do to the variable called muted? Change it from 1 to 0 or 0 to 1. That's all. So it's like turning a light switch on or off and remembering with a variable that I have done that. Meanwhile, on the right-hand side, in layman's terms, what is the purpose of the script on the right? To play the C line sound if he is not muted by nature of that variable. So we're sharing state, so to speak, sharing information across these two scripts, because notice here we are forever doing the following. If muted is 0, so if it's not muted, if muted is false, then play the sea lion sound and think to yourself, hi, 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 for 2 seconds, wait a moment, and then check again. So if we go now over here to the left where this guy is and hit this the green flag, at what point does this get really annoying? This will just go on forever. So sometimes infinite loops, so to speak, are deliberate. But in this case, as soon as I hit the spacebar, he stops. Now, the program has not quit. It's still running in these loops. But if I hit the spacebar again, he's going to pick up where he left off. So there's one way for us to do something again and again, but that time only conditionally. Well, while we're in this vein of doing things again and again, let me go into another such example here. This one we'll call counting sheep. And notice what this guy does. It's actually a bit more like the pseudocode we played with on Wednesday, whereby he sets some counter, think of it as n again, to 0. He forever does the following. He says the counter's value for 1 second, waits a second, and then changes the counter by 1. And in this context, that just means increments it. So he adds 1 to it. So this is literally, it's not quite what we think of as counting sheep. It's the sheep doing the counting forever up from 0. All right, so we could do similar things there logically. But now let's try to clean some of these things up. Let me go ahead now into a simple example where our cat is just going to start coughing. All right, so here we have cough 0. The computer scientists start counting from 0. So this cat is just going to cough 3 times. And here's how I implemented that. When green flag is clicked, cough, wait, cough, wait, cough, wait. And I did this just by dragging and dropping puzzle pieces. Or if you start to tinker with Scratch, you'll see you can actually duplicate pieces so that you can do things more quickly without dragging and dropping ad nauseum. But we're not on the best path here, because how do I make him cough a 4th time? Well, I could sort of go down here. I could duplicate and then paste this in there. How do I make him cough a 5th time? Well, copy and paste again or drag and drop again. And very quickly, this program starts to get really, really redundant, really long, but really uninteresting. But there's a way to clean this up. What's the obvious way to clean this up? OK, so we could actually really go all out and when you hit the space bar, have him cough. But if I just want to do something repetitively, recall that we do have some control constructs. Let me move this out of the way, go under control. Let me just do a repeat, say, 3 times. And now let me steal some of these puzzle pieces. Let me snap this in here. Let me throw these away altogether. And now I have a better designed program. Why? If I want to change the number of times this cat coughs, all I have to do is change one variable, or one value rather, from 3 to 4 or 5 or 6, or I could do something conditionally even with the spacebar if I wanted to. So this is a general principle. Once you start copying and pasting code, whether it's in Scratch or in C, you're doing something wrong, most likely, or at least once you've exceeded some reasonable numbers of copies and pastes, you're probably doing something wrong. But you know what? This is I don't really like this. This isn't the cleanest design. I wish there were a puzzle piece called cough, because then I wouldn't have to implement this myself the old-fashioned way by having say and wait. What if there were just a cough puzzle piece? Well, I can actually do that. Let me go under More Blocks, click Make a Block, and now I get this window here. I'm going to call this thing cough. I'm going to go ahead and click OK. And now notice I get a new starting piece that's curved on the top. And you know what I'm going to do with this? I'm going to just steal these blocks. I'm going to put them here. And now with these 3 pieces, I've implemented what I'm going to call a function or a procedure. Some of you might know it as a method. Slight differences among the words, but for now, let's just call this a function. This is just a new puzzle piece. Now, it is implemented like this, but notice that Scratch has given us a physical representation of that whole block over here. So now I can just drag this over here, say repeat 3 times, and what's going to happen now when I play this script is only one program is running at a time. There's only one when green flag clicked. But that purple block called cough is effectively telling Scratch every time you see that puzzle piece, actually execute these steps that I happen to implement manually. So that's kind of neat. But now suppose that I decided I don't want this cat just to cough. I want him to be able to sneeze as well. Well, how could we go about implementing sneeze? Well, I could pretty much do the same thing, right? I could make another block. I could call this sneeze, click OK. Then over here, I could actually have, let me duplicate this. And there's where you should feel like you're probably not doing something in the best way. I could say something like achoo for 1 second. Wait 1 second. Now I have a new block called sneeze, and indeed there it is. But this too should start to feel, maybe not the first week of class, but by the second, just a little redundant. Clearly, there's some redundancy here. So let me propose instead that we refine this definition as follows. Let me go up to my File menu. I'm not going to save this version. I'm going to go into one of my pre-made files here, and I'm going to go ahead and open up cough2. Whoops, that was cough2. Let me go ahead and open up cough3, which is in the source directory, cough3. And notice, I told the story in the wrong order. Let me recover from this story. The story I meant to tell ends with cough4. There it is. So what if I instead define a bigger puzzle piece called define say word n times, right? Sneezing is just, apparently in Scratch, achoo. So we express it as a word just because that's the constraint of the program. And a cough is but cough, C-O-U-G-H. So that's just 2 different words doing essentially the same thing. So I can actually make a new block like this. I didn't use this menu option before, but when you click Make Block, you can choose some options, and you can say that this block actually takes some inputs, otherwise known as arguments or parameters, so that you can modify the behavior of your block. So what I did a moment ago was I called this block say, and then I said it takes a string input, and now notice by default it says string1. A string is just a word or a phrase for our purposes, but I'm just going to put some placeholder text there, just like in a website when you see username or password and then it disappears when you start typing. That's all that is. And now I'm going to add a number input, and I'm going to call this n, but that's pretty arbitrary, and then just a label just to make this block a little more self-explanatory, times. That's what I just did. And the end result is that I get a block that looks like this. And now notice I'm using a repeat block, but rather than hard coding 3, I'm dragging and dropping n in there so I can parameterize the function. I can make this function do something a different number of times based on that value. And notice say, this is what I did here. If I drag word, I can say not a hard-coded word, but whatever is passed in for 1 second. Meanwhile, how do I re-implement cough? I instead define cough as saying cough n times. So in short, I'm going through this quickly, but the basic idea is as soon as you start seeing in your program that, wait a minute, I've done something quite like this before, can I factor out some common functionality? Can I decompose what I'm doing into some basic ideas? That's what we're doing here, and I've stacked these things visually on top of one another because it's testament to that idea of starting with binary, going to ASCII, making graphical programs, sort of layering increasingly complex ideas on top of one another. Same idea here. I started from scratch implementing coughing, then realized coughing is really just saying something. So let me instead implement the notion of saying something, and on top of that, can I implement achoo or cough. And we could do more such variants still. So from this basic principle, we can start to do increasingly complex programs. Let me open up this one. We can actually have multiple sprites interacting on the screen at once. If I go into my source directory and grab one called threads, recall that a thread is just really the ability of two scripts to run side by side at the same time. Notice now I have both a bird sprite and a cat sprite, both of which have their own scripts. So notice when I click the cat, I get these scripts. When I click the bird, I get these scripts. So each of these guys has his own programs. When I now click the green flag, notice that what this program does is have the cat incredibly slowly chase the bird. But the cat has the advantage of having been programmed in such a way that no matter where the bird is, the cat goes toward him. We can play that game much faster. So if I'm on the cat, notice that I'm using, let's say, move 1 steps. Let's have him move 5 steps at a time, so 5 dots at a time. Let me click play. All right, now we can really give the cat the advantage, 10 steps at a time. All right, so very quickly it gets a little advantageous for the cat. But I'll wave my hand at some of the details. But the reason that that path is starting a little different each time is that I'm doing a bit of randomness. I'm actually pointing the cat in a different direction based on where I want him to begin, so that each time the game or the animation is a little bit different. Now let me introduce one other construct here. So in this case, we had functions. There's also going to be a puzzle piece known as an array or a list that allows you to store multiple values inside of a variable. We saw threads, and now there's events. So here's an event using these two guys here. And if I open up the file called events from today's examples, we will see a program that looks a little like this. And now notice this guy, so notice I have the blue Muppet clicked. He only does the following. He doesn't have one of those green flag icon, puzzle pieces. He has a when I receive event. So some arbitrary word. I just typed out event there. He's going to say polo for 2 seconds. So those of you familiar with this game might know where this is going. If I now click on the orange Muppet, his program does this. Forever, if the keyboard spacebar is pressed, he is going to say Marco for 2 seconds on the screen, but he's also going to use this fancier block known as broadcast. He's going to broadcast, quote unquote, event. Meanwhile, the blue guy, recall, is listening for, quote unquote, event. So somehow now we can have two sprites interacting. And when we get to web programming later in the term, similarly, will this be advantageous to have your website do something in response to, for instance, a click of the keyboard. So let me go ahead and hit the space bar. Orange guy says Marco. Blue guy says polo. All right, if I do it again, orange guy says Marco. Blue guy says polo. So let's take this one step further. This time, we'll go probably just a few more minutes here. Do we have desk lamp? Come on down. You're right on the end. Okay. Okay, you can both come up. We have desk lamps for everyone. Come on. I don't know if we can keep this ridiculous gag up all semester, though. All right, come on down. And in the meantime, we have the following examples to pull up just to accelerate things now, such that we have a manifestation from another predecessor of yours using these same basic building blocks. What's your name?
John.
John, nice to meet you. And? Sets, yeah. Nice to meet you. John, if you'd like to come up first. This is an old school game named Frogger. You use the keyboard for this as well, and the goal is to get across the street and water. I'm sorry, no desk lamp for you today. All right, Sets, would you like to come on up? All right, May. All right, here we go. Let's do it again. Adjust the arrow keys, up, down, left, right. We'll call them consolation prizes today, then. Very well done. Here for both of you, John and Sets. Congratulations. All right. So again, As this game plays, think about what's going on. One, there's clearly a lot of motion, but we've seen how, with the cat and the bird example, how you can make the illusion of motion by just moving some number of pixels again and again. And if you have a forever block, you can have these cars doing this forever. We have the ability to have some randomness, so this game doesn't have to be exactly the same each time. Those logs, those cars can start at slightly different times so that the game itself is more interesting with each gameplay. And meanwhile, we've seen the ability to listen to the space bar, but clearly in Scratch, can you also listen for up, down, left, right, and really any key on the keyboard. And you can also do some other things. Let me go ahead and go back to the web version. Let me go into our collection of examples here. And under My Studio, which is essentially a folder on scratch.mit.edu, we have the web versions of all of these projects. And let's see if I can get my computer to cooperate here. This is written by one of our friends at MIT called Move the Butterfly. And once this opens up, this is going to actually use more of my computer's hardware. Scratch happens to be implemented with Flash. Flash can talk to your webcam if you have one. So if I go ahead and full screen this here, click the green flag, notice that Flash's security message is saying, do you want to allow it to use my webcam? Normally, you should probably say deny, but in this case, we'll say allow. Then I'm going to tell Chrome to allow this as well. And now in just a moment, you see me. Yep, me. And if my hand goes up, I got to not move my head at the same time. There's also a reflection on the screen. Come on. There we go. You can move it on the screen because there's also puzzle pieces. Oh, you know what it is? It's because you also see the projector screen behind me, so we have a little infinite thing going on there. All right, so I'll play down here. There we go. So there's also a puzzle piece that says when you see movement beneath one of the sprites, you can have it go up, down, left, right, or the like. So we have a bit of virtual reality going on here as well, all within the confines of my browser, just here using my webcam. So what's then on the horizon? The first problem set, as you'll see, the PDF will go online, or the website will go online later tonight at cs50.net, is pretty much going to be open-ended and implement a Scratch project of interest to you, a game, an interaction, something artistic, and challenge yourself to use any number of these puzzle pieces. And it can either be interactive in this way, or it can be something more deliberately made to tell a story. And indeed, that's where we'll end off today with one final example. Let me go into Scratch locally. Let me go ahead and open this and play one last program written by one of your predecessors, namely that one here. Good. Raise the volume for this one.
Weather girl. And have we got news for you? You better listen. Get ready, all your lonely girls, and leave those umbrellas at home. All right.
It's rising.
Rising.
I'm just getting low.
How low, girl?
According to all sources.
What sources now?
The street's the place to
We better hurry up. 'Cause tonight, for the first time, just about 10:30, for the first time in history, it's gonna start raining men. It's raining men. Hallelujah, it's
And with CS50, we will see you next week.
I'm gonna go out.
At the next CS50, David invites a volunteer
Demonstration,
on
we're gonna need
stage.
one volunteer. Would you like to come on down? What's your name? Moving on.